This conference will now be recorded.
Good afternoon, everyone, once again, and welcome to the live session for modules 5 and 6. I am Gina Alquiz Malacas, a faculty member of the Department of Mathematics and Statistics for 25 years now. Yes, I am celebrating my 25th year in the department. So before I go to my main task, let me remind all of you for the goal of this online bridging class. So our main goal is for you to prepare for your calculus classes. Take note that we are only instruments, but the best part, the biggest part is in you. So I suggest you have papers and pen with you. If you have papers now, I hope, so you can follow. Now let's go to the class. Kindly turn your microphone off, please. Okay, the objectives of my talk are first to define relation and function, to discuss some properties of functions and relations, and to discuss some aids in graphing a function or relation. All right, I presume you have already studied the modules given to you. I hope so, because what we will be discussing now are just supplemental modules. Let's go to the definition of relation and function. A relation R from a set X to a set Y is a rule that assigns to each element X of the set X at least one element Y of the set Y. And it is possible that X is equal to Y. So here in the relation, so you can think of the relation as your relationship with your special someone. But of course, there is a rule. What is that rule? The rule assigns each element in the first set at least one element in the second set. Okay? The set X is called the domain of the relation R, which we just call it R. You can actually name it using other letters. However, R is more convenient just to help us remember that it's relation, while the set Y is called the codomain of the relation R. Codomain is actually a shorter term for counter domain of the relation. So take note, X is the domain, Y is the codomain. The set of all Y in Y that is assigned to some X in X is called the range of the relation R. Remember, the relation R only emphasizes that every element in the first set has at least an element in the second set as its pair. So it doesn't say anything about the elements of the set Y. So there are possibly elements of the set Y that is not being paired with the elements in X. So only those elements in Y which are being paired with the elements in X constitute the range of the relation. Clearly, the range of any relation is a subset of its codomain. Okay. A function, however, from a set X to a set Y is a rule that assigns to each X in the set X one and only one element Y of Y. A function is a relation. It is a special relation because every element in X is assigned to exactly one element Y of Y, right? So we are now ready to go to other terms. Okay. So for the notations, we use letters F, G, H, capital F, G, and H, but these are not limited to these letters. Other authors use Greek letters, but we just have to clearly emphasize or clearly distinctly determine that those letters stand for functions. Now, the domain X of the function f is denoted by d sub f. I want to use the pen, so I'm all right. So we can use the notation d sub f, this one. The subscript refers to the function we are referring to. So if we refer to the function g, so the subscript is changed to g. So it will be d sub g. So if the function is clearly stated, we can actually eliminate the subscript. So the range of the function is denoted by r sub f. So this one. Okay, again, the subscript refers to the function we are talking about. Now, this notation, if you see this, refers to the function from x to y. So it is read as f is a function from the set x to the set y. If f assigns the element y in y to the element x of x, we write, actually some authors use this notation. Wait. I need to go back, but my pen is first previous. And I want to go back to my slide. Previous. Okay. All right. So some authors use this notation for x. Right. Okay. 10. So here, x. This arrow. You can see sometimes. I'm adjusting to the pen. Okay. You see notations like this in some books, and or y equals this one, this notation, y equals f of x, which is read as y is equal to f of x. So using this notation, the range of f can be described as this set, the set of all y in the set y such that y is paired to x. So y is equal to f of x for some x in x. Now, proceed to the next slide. Okay, an example of a function is described by this. A function f from the set, we only have a finite set containing the elements 1, 2, 3, 4, 5 for an easy illustration, is mapped to the set y containing the elements 0, 1, 2, 3, 4, 5 to 8, defined by the following rule. So 1 is paired to 0. So we write f of 1 equals 0, and then 2 is paired to 2. So we write f of 2 is equal to 2. 3 is paired to 4. So f of 3 is 4. 4 is mapped to 6. So f of 4 is 6. 5 is mapped to 8. So f of 5 is 8. Take note, our domain here is finite. It only contains 5 elements. So as you can see, our codomain contains 9 elements, but only elements 0, 2, 4, 6, 8 constitute the range. Now, there are several methods of describing relations or functions. So one is by mapping. So what do we mean by that? We can actually think of, we can represent set by this geometric figure, x, and then this is your y. So The elements, for example, if you refer to example 1, it has 5 elements. So 1, 2, 3, 4, 5. Okay. And then we have 8 here. So 0 and 9. 1, 2, 3, 4, 5, 6, 7, 8. So imagine those elements inside the set. And so 1 is mapped to 0. 2 is, I can't control. 2 is mapped to 2, like that. 3 is mapped to 4. So there's the diagram. 4 is mapped to 6. And then 5 is mapped to 8. Okay. So we can represent this as the function f. Usually we write, okay, f. So that is function using described as a mapping. But this is just convenient for actually sets which are small in cardinality. Okay, then let's proceed. Now I'm going to the next slide. So I'll just, oh, I still have to erase this one. So I need eraser. Sorry, I'm adjusting to the pen. Okay, so we can also describe relations or functions using tables. So this is the tabular form of the function in example 1. So we only have to write in the first row the elements of the set X. So we have 1, 2, 3, 4, 5, and then 1 is mapped to 0, 2 is mapped to 2, as you can see. So that is the tabular form. We also have relations or functions as a set of ordered pairs. Take note that if R is a relation from a set X to a set Y, there is a set of ordered pairs given by, okay, because of that rule, we have the ordered pairs XY in the Cartesian product of X and Y such that Y is mapped to X by R. Okay, now this set gives the precise and efficient description of any type of relation regardless of the size of its domain. So it's easier to be describing the set if we have domain with a bigger cardinality. So here, our example 1 can be written as F, set of ordered pairs, 1, 0, 2, 2. If you recall, if you were able to write the set, the function f in example 1. So you see this ordered pair. So you can see also the table. Now, because of that, we have alternative definition of relation and function using the set of ordered pairs. So a relation R from a set X to a set Y is a subset of the Cartesian product of X and Y, for which every X in X corresponds to a Y in Y if XY is in the set R, where X is the first component and Y is the second component of the ordered pair. So it's just a set of ordered pairs. Okay. Now, a function f from a set X to a set Y is a relation from X to Y for which no two ordered pairs in F have the same first component. Why? Because every element nga of the first set, of the domain is mapped only to a unique element in the second set. So there should be no two ordered pairs in the set which have the same first component. The most common method of describing a relation on the set of real numbers is through the use of equation. So take note, this R here please do not confuse yourself with the notation. Just have to familiarize and memorize the, it's just like human beings, diba? We have also people having the same names. So the R here actually, because my font, usually it is denoted by this one, like that. So that is a set of real numbers. Notation for the set of real numbers. So the R here, this bold R, is for the set of real numbers. Now, so the most common method is when you have a function on R is through the use of equation. So if you go back to example 1, given in set form, f, this set, the function can be defined by the equation y equals 2x minus 2. Take note that when x is 1, so you have 2 times 1 minus 2, so our y is 0. And if you have this one, if you have x is 2 here, 2 times 2, 4 minus 2, so that's 2, so you have 2, 2. So when x is 3, 2 times 3, 6 minus 2, so you have 3, 4. And so on. So when x is 4 and when x is 5. Excuse me. Now, so we can write our function in this form. So set of ordered pairs xy in the partition product of x and y such that y is equal to 2x minus 2. Okay. Now, if there is no mention of the sets x and y, we take the domain of the relation or the function to be the biggest. Okay, take note. We take the domain to be the biggest set in the set of real numbers of values of x for which y is well defined. Okay, so this one, we mean by well defined, meaning our y has a meaning in R. So how do we find the domain? So to find the domain, so here is a helpful procedure to find the domain. We solve for, excuse me, we solve for y in terms of x, and then we look at the form of the equation. We determine the biggest set of values of x for which the resulting expression in x is well defined. However, a value of x which will not give meaning to the resulting expression may still yield to a value of y when it is substituted to the original equation, the given equation. So, okay, I will try to erase my writings because I think it's giving you headache, sorry. So a value of x, may, even if after solving will yield no meaning to the equation. However, when it is substituted to the original equation, it can also, it gives a value of y. So that x can still be in the domain. We will have example of that later. Anyway. So I really need to shift from pen to normal and then, okay. To find the range, solve the equation for y in terms of x, okay, explicitly, and then again, determine the biggest set of values of y for which the resulting expression in y is well defined. So similar in finding, similar to the way we find the domain. Okay. So for example, so we're just giving you this simple example. Y, function f defined by y equals 4x minus 1. Find the domain and the range. So very simple. Since the function is, so first, the domain, the function is already written explicitly in terms of x. We just look at the form of the equation. As you can see, y it has meaning. This equation has meaning for all real numbers x. So there is no restriction to this. So our domain, the domain of f is just the set of real numbers. All right. Now, to find the range, we solve for x in terms of y. So we're given this, we solve for x. So you have 4x. You have this already. You had this already in your last session, so it's easy for you. Okay, and then we get x equals y plus 1 over 4. Again, if you look at the equation, this is well defined for all values of y. So the range of f is also R, the set of real numbers. Very easy. Now let me clear this one. And then proceed to the next example. Suppose you're given a function from the domain of the function f, which is a subset of the set of real numbers, defined by the equation below. So here we have y equals 2x plus 1 over x minus 3. So to find the domain, again, we look at the equation written explicitly in terms of x. So you have this. Now, this is a rational function. Okay, so when you encounter rational functions, you always remember that a rational function, it has meaning if the denominator is not 0. So yun lang. So you just have to look at the denominator. So if x equals 3, the equation has no meaning at all in R. So that is a restriction. So therefore, our domain is the set of real numbers minus the set containing 3. Or you can write this in interval notation form as negative infinity. I'm sorry. Take that out. Negative infinity to 3, excluding 3, union 3 to positive infinity. So that's how we write that in interval notation form, this set here. Okay. Now, how to find the range? Again, we solve x in terms of y. So we get y times x minus 3. We can do that because x minus 3 is not 0 after all. So we can multiply both sides of the equation by any non-zero quantity. So we can do that. That is legal. So now we distribute. So we get xy minus 3y equals 2x plus 1. I hope you can see clearly my handwriting on the screen. So we combine terms with x. So you get xy minus 2x equals 3y plus 1. Factoring out x, we get y minus 2 and then this is equal to 3y plus 1. So dividing both sides by y minus 2, we get 3y plus 1 over y minus 2. Okay, so now if you look at the equation, it's a rational expression, and it has meaning except when y equals 2. So therefore, our range, the range of the function, is equal to the set of real numbers minus the set containing 2. Okay? Or in interval notation form, this is negative infinity to 2 union 2 to positive infinity. Okay, so before we proceed to the next example, let me erase this. So I hope you have already copied for those who want to review later your work. So we have erased this one. Okay, now let's proceed to the next example. Let's see. Again, normal. Okay, next. So look at number 3. Can you try this one alone? So you have a function from d sub f to r defined by the equation y equals square root of x minus 1 over x. So we have here a radical expression. Okay, so as you can see, y is written explicitly in terms of x. So it's easy to write the domain. So our domain, but not that easy because we have to look at the radical. Okay, so we have y equals square root of x minus 1 over x. Remember, you have a radical here and a rational form of the radicand. Okay, now a radical of index 2 is defined if the radicand is greater than, so this is well defined if x minus 1 over x is greater than or equal to 0. So this is an inequality problem now. So if you recall in the last session, the boundary points here are when x is 0, the roots of this, no? X minus 1 equals 0. So x is 1 and x is 0. So you have 0 and then 1. Okay, so we can divide the real number line into subintervals from negative infinity to 0, excluding the 0, and then 0 to 1, including 1. Why do you have to include 1? Because it will still satisfy the inequality here. And then we have 1 to positive infinity. So we can get test points. So when x is, say, negative 1, substitute it here. So you get negative 1 minus 1, that's negative 2, over negative 1, that's positive. So that is greater than 0. And then when x is 1/2 here, you can take 1/2 as a test point, test value. So you will have when x is 1/2, this is negative, this one is negative 1/2 over 1/2, that's negative. So this is less than 0. And if you have a point here, let's say 2, 2 minus 1, that's 1 over 2, that's greater than 0. So therefore, these two intervals here satisfy our inequality. And so therefore, our domain, the domain of f, is equal to negative infinity to 0, excluding 0, because it will make the denominator 0, union 1 to positive infinity. Okay, so that's our domain. Now, how do we find the range? Okay, are you good? Are you still there? I saw someone leaving the group. Well, like I said, we're just here to give you the opportunity to learn. If you don't take it, it's not our loss. If you are bored, if you are tired, if you are disappointed, think of the people who have sacrificed for you. Just a reminder. So let's go back to the lesson. We solved for x in terms of y. So how do we solve this one? From the previous discussion, if you have a radical equation of index, one have to remove that with square. So we have y squared equals x minus 1 over x. Now we multiply both sides by x, so we get x y squared equals x minus 1. We combine terms with x, so you get xy squared minus x equals -1. Factor out x, so we get x, and then y squared minus 1 equals -1. So x is equal to -1 over y squared minus 1. So what will our range be? Okay, I hope your guess is as good as mine. So we have here x equals -1 over y squared minus 1. So range of f, this is well defined for all real numbers except when y is this one here below. Y, you look at the denominator. That's when the denominator is 0. That's an exception. So we have plus minus 1. So this set. In interval form, you can write negative infinity to -1, excluding -1, union negative 1 to 1, union 1 to positive infinity. Okay, so that's it for the domain and the range. We proceed, but let me erase this writing first. Then change to normal. Okay, so we have next slide. Now, if you have a relation or function, a relation rather, described using an equation, one can determine if it is a function or not. So you use this criterion that if for any two elements A, B in the domain, and A is equal to B, this one, then R of A, the images are also equal. We call this images, image of A, image of B. So the images are equal. So for example, let G be a relation defined by this equation. Show that G is a function. All you have to do is start from here. So you'll have suppose, okay, let A be in the domain of G such that A is equal to B. Then this cute little thing called equality allows us to square both sides and retain the equality. So therefore, we have A squared equals B squared. And then we can also multiply both sides by -1. That's the property of this cute little thing called equality. That's its property. So you have this. And we can also add both sides by 3, any constant actually. But specifically, we add 3 because we want to get the form of the equation. So you have -b squared plus 3. So as you can see, this is G of A. And this is, the right side is also g of b. So therefore, we started from a equals b and ends up with g of a equals g of b. So therefore, g is a function. Function, okay? That's it. Then we clear the board. I miss my board. I miss our board, actually. So clear. And we go to, not yet, change to normal. And then we go to the next slide. Okay, the relation now here. How do we show that given relation is not a function? So all we have to do, how do we show that it is not? We can only disprove by counterexample. So all we have to do is to take counterexamples. So we have take, what do you think? You can take, okay, x1, wait, x1 equals 4, which is equal to x2. So our x1 is 4, our x2 is also 4. And when we can take y1 equals 2, and then y2 equals -2. So these are our, so we have these points 4, 4, 2, and 4, -2 in R. So these 2 points are elements in R. But note that x1 equals x2, but y1 is not equal, the images is not equal to y2. So therefore, R is not a function. Okay, so then we go to the next slide. So we also have relations and functions defined by a graph. So what is a graph? The solution set or locus of an equation involving two unknowns, say x and y, is a set of all points in the plane, in the Cartesian plane, that satisfy the equation. And the geometric representation of the solution set is called the graph of the equation. Hence, if R is a relation described by a set, capital R, of ordered pairs, the graph of R is a set of all points x, y in R squared. This is R squared. This one, R squared, for which xy here is in R. Take note, this x is not the same as this x, please. And then this R is not the same as this R here. This R represents our relation, and this one is a set of real numbers. Do not confuse yourself, because notations in mathematics are actually very useful, and they make math even more beautiful. So in other words, the graph of the relation R is a picture of the set R in the Cartesian plane, okay, in R squared. Okay, and then we look at, our example earlier, example 1. If you look at our example, we, let's, I'm sorry, pen. I need to go to erase and then go to pen. Okay, so this is our function in example 1. As you can see, our domain is finite, but you can still plot the function, sketch its graph. You have x equals 1, 2, 3, 4, 5, and this is the defining equation. So when x is 1, y is 0 here. When x is 1, y is 0. So we have this point. Oops. When x is 2, y is 4. 2, sorry. 2, 4, 6, 8. Okay. So when x is 2, y is 4. When x is 3, y is no. When x is 2, y is 2. Sorry, it's here. Not this one, please. When x is 3, y is 4. So actually, the points follow a straight line. When x is 4, so that is 6 here. But it's not a line. It's just forming a line because our domain is discrete. It contains only the elements 1, 2, 3, 4, 5. Okay, very easy illustration just for you to easily follow. Okay, so you can easily follow. Then we can also use the vertical line test for functions. So if you're given a relation or a function used in graphically, so in other words, the sketch of the graph is given, you can check whether it is a function or not using a vertical line test. You only have to draw a vertical line. For example, if you are given this function, say for example, no, this graph, so you can draw vertical lines, and if it intersects the graph at most once, then that is a function. So for example, this one here, that is not a function because if you try to test using a vertical line test, it intersects the graph at 2 points. So it does not satisfy the definition. So that's it. And then you can we also have some functions with their special names, but we only give um, several examples. We have plenty. We have trigonometric function, hyperbolic function, exponential functions, and a lot more. It depends on the defining equation, the form of the defining equation. So first we have the polynomial function, an nth degree polynomial function. This is very general of this form. This one, where n is a non-negative integer. That is a polynomial function. And special cases are the linear functions and the quadratic function. Of course, you take note of the defining equation, you look at that. So a linear function is given by this equation. And this equation has a graph that is a line. And then we also have this quadratic function whose equation is given in this form: y equals ax squared plus bx plus c, where a is not 0, a, b, and c are constants. Okay, so we also have the absolute value function that is defined by the equation y equals the absolute value of p of x, where p of x stands for any polynomial in x. So as an example, sorry, the pen is not so friendly with me. So for example, function defined by the equation. Okay, this one. So if you recall the definition of the absolute value, this is just x if x is greater than or equal to 0, negative x if x is less than 0. However, this is just a very simple absolute value function. but this px here can be any of the form of any polynomial. Okay. Then we go to the rational function. Erase. Okay. So a rational function is of the form, of course, if you have a function of the form over q of x like that. So an example is if you have this one, x, the one that we had also earlier, finding the domain. So that is a rational function. Okay. Are you still there? I hope you were not leaving. Okay. You're still living, not leaving. All right. So this one is, we also have the piecewise function. Okay, so this looks scary, but this is very simple. Suppose we have a function f defined on the domain d sub f, but the domain can be partitioned into subintervals. So we have a partition of the domain. So if you recall, the rational function, I mean the absolute value function, this one, which is written, that is an example of a piecewise. So this is if x is greater than or equal to 0, negative x. That's why I wrote it, because I want to cite it as an example of this piecewise function. So this one here, if you look at that, is a partition of the domain. Our domain actually here is R, and it is partitioned as this one, negative infinity to 0, union 0 to this one, to positive infinity. So that's a piecewise function. Okay, now we go to the properties of functions. So when do we say that a function is onto? So a function f is onto if each element of y has at least one element of x mapped into it. So in other words, every element in the second set, the codomain, is used up. So it's being paired with the elements of the set x. So that is what we mean by an onto function. While, by the way, examples are all non-constant linear functions on R. So if you have a function, linear functions on R, those are onto functions. The constant function, however, is not onto unless we limit our counter domain to one and only one element, that constant which is being mapped to. So it becomes onto. Next is a function is one-to-one if each element in the range of f has at most one element of x mapped into it. Equivalently, we can define a function f to be one-to-one whenever we have two elements x1, x2 in x, and x1 is not equal to 2, to x2 rather, implies their images are not also equal. But it is more convenient to use its contrapositive. So what will be the contrapositive of this? So we will have if f of x1 equals f of x2, then x1 equals x2. That is more, actually more convenient. So how do we determine whether a given function is one-to-one or not? Okay, first, to show that it's not one-to-one, just like showing that the relation is not function, we can take counter examples. You pick two elements which are not equal, and then they have equal images. That's one, showing that it's not one-to-one. However, to show that the function f is one-to-one, we assume that the images are equal and then show that their pre-images are not equal. So, example, this one, show that this is one-to-one. The function is one-to-one. So how do we do that? Again, we prove this one. Proof. Okay, suppose that f of x1 equals f of x2. Therefore, this implies that we have 4x1 minus 1 equals 4x2 minus 1. Remember this little thing equality called equality? Okay, we can add both sides by same constant, so we can add by 1, so you get 4x1 equals 4x2, and then we divide by 4, so therefore we have x1 equals x2. So we started with this and then ended up with this. So therefore the function is 1-to-1. Okay, of course you will encounter more complex form of the equation in the future. But however, if you know the process, you should not be afraid. Okay, so we go to the next. Okay, now we show that the function given by y equals 2 minus x squared is not 1-to-1. So again, how do we do that? We take counterexample. So what do you think will be our counterexample? So we can take what? Okay, counterexample. So we can take x1, sorry, how do I erase this one? Take x1 equals 2, and then x2 equals -2. So what is f of x1? So we get 2 minus 2 squared. That is -2. And what is f of x2? So we get 2 minus -2 squared, and that is also -2. So we have here two equal images, but not equal pre-images. So therefore, those are counterexamples, and G is not, sorry, this is G. It should not be F. We're referring to our G here. So G, okay. So G is not 1-to-1. Okay, are you still there? So even if you don't stay, I still need to proceed. Okay, wait. Then we look at the inverse function now. If f is 1-to-1 and onto, then there is a function called the inverse function denoted by f. This is read as f inverse. And we call it the inverse function of f, where the associated set of ordered pairs is given by this set. Okay, take note that it is a requirement that f is 1-to-1 and onto for the inverse to exist. Now, in the previous example, we have shown that y equals 4x minus 1 is 1-to-1, and we have shown that it is also onto. How did we show that? Well, there was a remark earlier that any linear function on R is onto. So y equals 4x minus 1 is a linear function, so that is onto. Now, we find the inverse. How do we do that? If you look at the definition clearly, the domain of the inverse is the range of the function f, while the range is the domain of f. So we interchange the role of x and y. Interchange the role of x and y. And then we solve for y in terms of x. So you have x equals 4y minus 1. I hope you can read it clearly. And then we solve for y. So you get 4y equals x plus 1. So we get y equals x plus 1 over 4. So therefore, f inverse of x is equal to x plus 1 over 4. Easy, very easy as eating durian, okay, without peeling it. Okay. So we have now we look at the composite function. So given two functions f from the set x to y and g from y to the set z. Take note, you have three sets here involved, x, y, and z. The composition of f and g is the function g circle f from x to z given by g circle f of x, this one, equals g of f of x. So graphically, we can look at the composition function here. Okay, if you look at the screen, you have the set x, the set y, and the set z. You have the function f from x to y, and then you have a function g from y to z. Now take note that the range of f is a subset of the domain of g. Now it is, like I said, it is required that the range of f is a subset of the domain of g. We also call the composition function as the composite, no, for a simple term, composite function, g circle f. So example, given the functions f and g and r on the set of real numbers defined by the equations y equals 2x squared plus 1 and y equals 3x minus 1. Okay, so what is the domain of f? As you can see, it's a set of real numbers because it's defined for all r, and the domain of g is also the set of real numbers. And the range, if you look at the range of the function f, if you solve, no, we don't have much time, we still have to go to graph sketching. If you look at the form, you can see that the range of f is the interval from 1 to positive infinity. Now we find the composite function g circle f. Okay, so g circle f of x is equal to g of f of x. So we get g, what's our g here? 3x minus 1. So 3, our x is f of x. So f of x minus 1. And so we get our f of x is 2x squared plus 1. So 2x squared plus 1 minus 1, and this is equal to 6x squared plus 3 minus 1. Therefore, this is equal to 6x squared plus 2. Okay, so that is our G circle F. Okay, very easy. Okay, now we go to sketching of the graph of some functions and relations. Now, there are functions and relations which do not have what you call closed form, like linear. We always remember that linear functions have lines as their graph. Quadratic functions have parabolas as their graphs, while other functions, sine functions, cosine functions, they have closed form. However, there are other functions, like I said, that do not have closed form. So how do we sketch the graph? Of course, we need to look at some information. Those are aids in graphing. First, we need to know the domain. Of course, which values in R will have pairs in R as well. So, and then we also have to look at the range, because those values of the domain and the range will constitute the locus of uh, the points in the solution, right? So that those will consist the points in the graph. And then we also look at the intercepts. These are the points that intersect the the graph intersect the axis. So an x-intercept is a point at which the graph crosses or touches the x-axis. Any y-intercept is a point at which the graph crosses also the y-axis. To find the intercepts, let's just recall we had this since kindergarten, how to find the intercepts. Okay, that's kindergarten lesson. To solve for the x-intercept, set y to 0 in the given equation and then solve for the value of x. Now, if x is equal to a, then a0 is the x-intercept. Remember, x-intercept is a point. To solve for the y-intercept, set x to 0, and then solve for the value of y. So if y is equal to b, then 0b is the y-intercept. Okay. We also have the symmetries, or the mirror-like property. So suppose uh, you have a point here in the first quadrant, and then if the graph is symmetric with respect to the x-axis, this is the x-axis, then there must be a point in here equidistant from the x-axis. So that is when the graph is symmetric with respect to the x-axis. However, with respect to the y-axis, if it has a point here, and if the graph is symmetric with respect to the y-axis, then it should have also a point here. With respect to the origin, suppose you have a point here, then the graph should have a point here. If it is symmetric with respect to the origin, it should be equidistant from the origin, this point and this one. These two should be equidistant from the origin. Now, how do we test for symmetry? Okay, so we have, how do we do that? Replace y by negative y in the given equation. Now, if the resulting equation is equivalent to the original, then the graph is symmetric with respect to the x-axis. However, if we want to test for symmetry with respect to the y-axis, so it's the y-axis, so therefore we replace x by negative x, and x here by negative x. So if you have x and then x negative x here, so if it results to the same equation, then the graph is symmetric with respect to the y-axis. With respect to the origin, you need to replace uh, x by negative x and y by negative y. So if you have a point here, x, y, then you need to replace it with negative x, negative y. If it will result to the same equation, then the graph is symmetric with respect to the origin. Okay. What else do we need? The asymptotes. Let's erase this one. we're almost done. Okay, so the asymptotes, a line x equals k, where k is a real number, okay, is a vertical asymptote to the graph of an equation if the distance between the graph of the equation and this line is getting closer to 0. That is, the graph or a portion of the graph is getting closer to the line x. So they almost, the line almost, I mean the graph almost touches the line, but actually never touches it. However, somewhere, probably it can cross the line in some other parts, but most of the points actually get closer and closer to the line. So similarly, for the horizontal asymptote, you have a horizontal line that has the same property as the vertical asymptote. And then, how do we find vertical asymptote and horizontal asymptote? So very easy. Solve the given equation for y in terms of x. So remember that when we find the domain, we solve for y in terms of x. So that's easy. We have already solved that one in the first part. Remember, the first that we're going to do is to find the domain. So just look at that equation and check for the values for which the denominator becomes 0, but the numerator is not. Similarly, for the horizontal asymptote, you solve for x in terms of y, and then you check on the values of the denominator that will make the denominator 0, but the numerator is not. Those will be the vertical and horizontal asymptotes. Example. Okay, actually this is found in the module 6, the last example of the module 6, and I presume you have already solved this one. Find the domain, range, intercepts, symmetries, and asymptotes of this relation given by this equation, and then give a sketch of its graph. Now, in some books, you can see instructions like discuss the domain, range, intercept, symmetry. So when you see the word discuss, it's actually finding those terms, domain, range, intercepts, like that. So let's start with the domain, and you are now very skilled in doing it. So how do we find the domain? So let's look at the equation. X y squared minus 4 minus 2y equals 0, 0. So if you look at the equation, you solve for y in terms of x. Now, no matter what we do by transposing some terms, we cannot solve for y in terms of x. However, we can see that the left expression is quadratic in y. So if you rewrite it in the standard form of the quadratic, you have x y squared minus 2y minus 4x equals 0. So here, our a is x. This is our b. Our b is negative 2. And our c is negative 4x in the quadratic formula. So you have a y squared minus by plus c equals 0. Okay, so that's quadratic in y. So we can, because this is not factorable, and we can only do this by completing the square or by quadratic formula. So it's easier to use the quadratic formula. So you have y equals negative b. So our b is negative 2, so 2 plus minus square root of negative b squared, that's 4, minus 4, a is x, and our c is negative 4x, all over 2x, which we can simplify further as 2 plus minus square root of 4 plus 16x squared over 2x. Now, if you look at the resulting equation, you know that the radical, here, the radical, you look at the radical expression, is defined for all values of x in the real number, in the set R. So because 4 plus 16x squared is always greater than or equal to 0. So that is always defined. Remember, 4 is positive, and x squared here is always positive, and you have plus 16x squared. So we don't have problem with the radicand. But if you look at the denominator, this has meaning if x is not 0. So here, x equals 0 is an exception. So x should not be 0. Now, you might be tempted to write the domain of the relation as set R minus a set containing 0. However, if we substitute to the original equation x equals 0, you get this, y equals 0. So therefore, 0 is being paired with 0. In other words, 0 is still in the domain. So therefore, our domain, the domain of the relation is R. Okay, you see, very easy. And then we look at the range. So if we go to finding the range, to find the range, so let's go to the range. So we have to find the range. How do we find the range? To find the range. Okay, the range, pen, the range. So we solve for x in terms of y. So we get x equals 2y, very easy, y squared minus 4. So this is our resulting equation. If you look at this, this has meaning except when y equals 2 and y equals negative 2. So our range actually is range of the relation is equal to the set of real numbers minus the set containing plus minus 2. So that is our range. So take note, our domain is R, and this is our range. Now, next is, so this is our B. A is domain, B is finding the range. And then we go to finding the test for, no, actually the order is not necessary, but we just have to follow the order of our discussion. So we look at the intercepts. So if we look at the intercepts, all right, the intercepts. Okay, so erase. So if you look at the intercepts, pen, okay. So first is the x-intercept. So how do we get the x-intercept? X-intercept, set y to 0. Y to 0. So what is our equation again? Go to previous. Okay, our equation is, we'll just do it here. So I don't need to copy the equation. So we have intercepts. Okay, intercepts he doesn't know. We have x-intercept, so we'll have set y to 0. We're almost done anyway. So we have when y is 0, so we get x 0 minus 4. You look at the equation, this equation here, please class, and then minus 2 times 0 equals 0. So we get negative 4x equals 0. So x is 0. So therefore, 0, 0 is an x-intercept. And then to solve for the y-intercept, please do not be as messy as this when you submit your task. My solution is so messy, but I would appreciate if you make yours not as messy as this. So y-intercept, so you set x to 0. So when x is 0, you get negative 2y equals 0, of course. 0, 0 is the origin. So that is also, the origin is a point in the x-axis and in the y-axis as well. So as you can see, 0, 0 is the only intercept. So we have, this is the y-intercept. Now next is to test for symmetry. So to test for symmetry, okay, erase. So these are D, symmetry. Actually, I prepared a slide for symmetry, but I will be losing the equation, so I need to refer to the equation. So symmetry, with respect to, first, with respect to, you read this as WRT is with respect to the x-axis. So with respect to the x-axis, what do we replace? Replace y by negative y. Okay, that's it. So we have x negative y squared minus 4 minus 2 times negative y equals 0. And we get x y squared minus 4 plus 2y equals 0. This is different from the original. So different from the original, not the same from the given. So therefore, it is not symmetric with respect to, therefore, the graph is not symmetric with respect to, is not symmetric with respect to the respect to the x-axis. Okay, who was that? Letter B is with respect to the y-axis. So with respect to the y-axis, what do we replace? We replace x by negative x. So we replace x by negative x. So we get negative x y squared minus 4 minus 2y equals 0. And we have x y squared minus 4 plus 2y equals 0. If we multiply both sides by negative 1. And this is different from the given. Different from the given. From the given. So we have given. So therefore, it's also not symmetric with respect to the y-axis. Now, with respect to the origin, Okay, let me turn your mic off. Okay, with respect to the origin, what do we need to replace? Replace x by negative x and then y by negative y. Okay, so we have negative x and then negative y squared. Refer to this equation here. Minus 4 minus 2 times negative y equals 0. So we have negative x, y squared minus 4 plus 2y equals 0. And if we multiply by negative 1, we get x, y squared minus 4 minus 2y equals 0. So we have the same as the given, right? So same as the given. So therefore, the graph is symmetric with respect to the graph is symmetric with respect to is symmetric with respect to the origin. Okay, so we now have information. What is it again? The domain is R, the range is R, minus the set containing plus minus 2, and the origin is the only intercept, and the graph is only symmetric with respect to the origin. Now we look at the asymptotes. Okay, letter F, no, letter E, asymptotes. Okay, so for the asymptotes, what is it again? How do we do it again? Okay, so first we have the vertical asymptote. We just write it as VA. Vertical asymptote, we look at the equation earlier when we solved for the domain. Remember, we have something like y equals constant here, 2 plus minus square root of 4 plus, there's a constant here that's almost, okay, like that, 2x. So if you look at the value in the denominator, if you look at the denominator rather, the expression in the denominator, the value 0, the value of x that is 0 is making the denominator, of course, 0, but it's not making the numerator 0. So therefore, x equals 0 is a vertical asymptote. Okay. Now, for the horizontal asymptote, okay, you recall that you have expression like something like there's an expression here and then y squared minus 4 like that in the denominator, and y equals 2 makes the denominator 0 but the numerator is non-zero. So we have y equals negative 2 and y equals 2. Just look at the equation that we had when we solved for the range. Okay, so we have these informations. Now we are ready to sketch the graph of the relation. Okay, so we go to graph sketching. Okay. Sorry. Okay, how do we sketch the graph? Wait. Why am I'm almost done. Why do you have to make me? Okay, so let's look at why it's not turning to pen. Okay, so let's see. We have the y-axis here and the x-axis here. Okay, let us recall that our domain is R. So it's possible that our graph extends from the left to the right because our our domain is R. And then our range is R minus 2. We start with the intercepts. So this is our intercept. Why can't I point the origin? So that is our only intercept. And then we start with our asymptotes. We have the horizontal asymptotes, y equals 2. Do not give me 2 as an asymptote. An asymptote is a line. So you have to write it as y equals 2, not 2. Okay, so y, strictasimum. Okay, 2, and then negative 2. So asymptotes are usually represented by broken lines, dashed lines. Okay, so this is our horizontal asymptote, and then this one. Okay, and then we have x equals 0 as the vertical asymptote. So this one here, okay, vertical. As you can see, the graph crosses the vertical asymptote somewhere, but some points here, many of the points actually are getting closer to this vertical line x equals 0. Excuse me. Now, next thing to do is we assign values, of course. So uh, we can look at values. What is that again? What's our equation again? X equals, I need to go back to the equation. X equals 2y over y squared minus 4. And then this is our y. So y, let's just say greater than 2. Start with greater than 2. Then y above 2, and then between 2 to negative 2, and then below negative 2. So let's look at some values here. You can think of y equals above 2. Let's say 3. So y is 3. You have 6 over 9 minus 4. So when y is 3, you have 6 over 9 minus 6 fifths. So when y is 3, so you have 6 fifths, 3. So let's just say 1, 2, 3. 3. 6 fifths is 1 and 1 and, I know, sorry, 3 here, 3. 1 and 1 fifth. So 1 and 3 here. So let's just say 1 and, sige na lang, na lang. It's hard to erase. Okay, suppose these are 3 here. So 1 and 1 fifth. So here, somewhere, 3. Okay, there's a point in here. And it is symmetric with respect to the origin, so we expect points somewhere here also, below. As if you can see my hand, trying to put, pointing those points there. If x is, say, 5, let's say 5, and then you get 10 over 25 minus 4, that's 21. 10 over 21. So it's getting closer here. So it's asymptotic here and asymptotic to the line x equals 2. And of course, because it's symmetric with respect to the origin, you would also expect some graph in here with respect to the origin. Something like that there, similar to that. And then here, we have between negative 2. When y is between negative, that information is very important, that information that the graph is symmetric with respect to the origin, because plotting some points here will give us an idea that there are also points in here. And then we have some points, we take some points between negative 2 to 2. Okay, so we have when y is let's say between -2 to 2. Okay, give me some values as if I can hear you. This is our x. Okay, so suppose we have x equals -1, -1, and no, rather y equals -1. That's between -2 to 2. So -1, we have -2 over -3. So this is 2/3. So when y is -1, then x is 2/3. I'm ng -1 here. Here, this is -1. This is 1. Okay, then x is 2/3. So somewhere here, 2/3. Okay, this is my graph on the screen. Look like a graph. Okay, so this is it. And then we have when y is 1. So when y is 1, we get here 2 over, so -2/3. X is -2/3. So 1, -2/3. So if this is our -1, so -2/3 is here. So that's, does it look like? Okay. So this is asymptotic. Actually, if you continue, you can form some points. Let's just say if you add more, let's say 1/2. When y is 1/2, you will get 1, 2 times 1/2. That's 1 over 1/2, and this is 1 over 1/4 minus 4. That's -3 and 3/4. Okay, so when y is 1/2, so 1/2, 1/2 here. There's a 1/2 here. So -1. This is -3 and 3. -3 times 3/4. That is a -15 over 4, so 4 over something. So actually, you can, if you continue, you can use your calculator. It's not as easy as sketching the graph as this, but it becomes easier because of those aids in graphing. That's it. That's just one example. You can have more. There are other examples that you can follow. Just keep on practicing. You can, if you will be able to solve all the examples given to you in the modules without looking at the solution, just do it by yourself, then you are set for the calculus class. Okay, good day. That's the end of my discussion. Have a nice day.